Welcome to The Explainer. You ever wonder how a roller coaster really works? Or what it takes to launch a home run? Well, it all comes down to one of the most powerful ideas in science, the physics of work and energy. It's kind of like a hidden language that describes why things move, and today we're going to decode it together. Okay, let's just dive right in. Take a look at this cyclist. They start out with some speed, they travel 600 meters over these crazy hills, and they end up at a totally different speed. All the while, they're fighting against air resistance, road friction. I mean, with all that going on, how in the world could you possibly figure out how much effort they put in? It just seems like a total mathematical nightmare. But here's the thing, it's not. There's this incredibly elegant principle that connects the start of the journey to the end. And to really get it, we need to start with a concept you think you know, but which has a very, very specific meaning in physics: work. So let's tackle that first idea. In everyday life, work means sitting at a desk, maybe studying for an exam. But in physics, the definition is way more precise. And it's all about just two things: force and distance. See, work is all about transferring energy. It happens when you apply a force that actually makes an object move. And the formula is beautifully simple. It's just the force you apply multiplied by the distance the object moves in the direction of that force. And this is the absolute key. Both the force and the movement have to be there. I mean, you could push against a solid brick wall until you're blue in the face, but if that wall doesn't budge, you have done zero, and I mean zero, physical work, because the distance is zero. But if you push a car and it actually moves, now you're doing work. And according to our source material, pushing with 1,000 newtons of force for 50 meters means you've done a huge 50,000 joules of work. Okay, so work is how we transfer energy. But what is energy? Well, for our purposes, you can think of it as existing in two fundamental states that are always trading back and forth with each other. So on one hand, you've got potential energy. This is just stored energy, right? It's waiting to be unleashed. Like this slide says, lifting a cat gives it gravitational potential energy. The higher it goes, the more potential it has. And on the other side of the coin, you have kinetic energy. This is the energy of pure, unadulterated motion. That raging bull, that is all kinetic energy. And this just perfectly shows the raw power of kinetic energy. The source material gives us this awesome example. A 700-kilogram bull, that's over 1,500 pounds, charging at 10 meters per second. That's about 22 miles per hour. So when you plug those numbers into the kinetic energy formula, you find out that bull is packing a massive 35,000 joules of energy. Now, to put that in perspective, that's the same amount of energy it would take to lift that entire bull 5 meters straight up into the air. And that's all just from its motion. All right, so we have work, which transfers energy. And we have energy in two forms, potential and kinetic. So how do they all connect? How does this solve our cyclist problem? Well, this is where it all clicks into place. Now, I know this slide might look a little intense with all the symbols and stuff, but just focus on this one equation right here. This is the key to everything. It's called the work-energy theorem. And here's the secret. It's not really some complex physics formula. It's just an accounting principle. Let's make this super simple. Just forget all the physics for a second and think about money. Think about your bank account. Think of it this way. The energy you start with, your kinetic and potential, that's just your opening balance. Any work you do on the system, like our cyclist pedaling harder, that's a deposit, a paycheck. But any work done by the system against things like friction or air resistance, that's a withdrawal. Think of it like an energy tax. And what you're left with on the other side, that's your final balance. That's it. It is a perfect accounting of every single joule of energy. So this whole energy accounting idea sounds pretty neat, but does it actually, work in the real world? Let's take our master equation and put it to the test with a classic physics problem straight from our source material. Okay, so what we've got here is a particle. It's starting from a dead stop at the top of a rough 10-meter-long ramp. The question is, how fast is it going to be moving when it hits the bottom? Now, that diagram on the right shows exactly what's going on. Gravity is pulling it down, right? That's turning potential energy into kinetic. But friction is fighting it the whole way. That's our work out. It's that energy tax being taken out of the system. So if we use our energy accounting method, the process is actually pretty straightforward. First, we figure out the initial potential energy. That's our opening balance. We know the final energy is going to be all kinetic because it's moving. Then we just have to calculate the energy that got withdrawn by friction. After that, we just plug all those numbers into our mastery equation and solve for the one thing we don't know, that final speed. And voila, here's the solution. When you actually run the numbers, the master equation tells you that the final speed has to be about 7.45 meters per second. It's not magic, it's just balancing the energy budget. You take the starting potential energy, you subtract the exact amount that was taxed by friction, and this is what you get. And here's the really cool part, the crucial point. This isn't just for some particle on a ramp. This exact same logic solves the cyclist problem we started with. It works for a car accelerating up a hill, a box sliding across the floor. It is a universal key. So, what's the big takeaway here? What have we really learned? Well, it's way more than just a slick way to solve physics problems. It's actually a deep, profound truth about how the universe itself works. This is the law of conservation of energy. And it says that energy is never ever created or destroyed. It just changes hands. It can be converted from potential to kinetic, it can be added by the work you do, or it can be withdrawn by friction into heat and sound. But the total amount in a closed system, it is always, always constant. It is the ultimate accounting system. Seriously, just look around you for a second. The light coming from your screen is energy. The sound hitting your ears is energy. The warmth of your hand is energy. It's all the exact same currency, just constantly being exchanged, all governed by one simple, unbelievably elegant rule of accounting. The real question is, now that you know the rule, where do you see it happening?